Hey, Science 30s, and welcome to our first of our two-part discussion about topic 1.4 electric circuits. Today I'm going to introduce the concept of what an electric circuit is, and then on the next video we'll dive into how we draw circuits and how we can analyze resistance, current, and voltage on these circuits. So for starters, last video we discussed motors and generators, and both of these provide or require an electrical current to basically to either power an electromagnet in the motor to spin, to make that armature spin, or in the case of the generator, we're going to create a current that is then going to be taken away to be transferred to another location to be utilized. But regardless of whether the current is going into the device or out of the device, whether it's a motor or a generator, these electrical currents that we either use or generate, they require a complete path. And the complete path in which these electrical currents flow, and essentially this is, as I mentioned at the very beginning of the unit, this is dealing with the flow of electrons. These electrons require a complete path to flow through in order for them to actually move. And we call that complete path a circuit, or in this more specifically, an electric circuit. An electric circuit, generally speaking, has four main parts. You're going to have a conductive wire that's basically connected from start to finish, in which the electrons can flow. There needs to be a source for the electrons, which would be, in this case, I've drawn a battery. And on this diagram, I'm using what are called schematic diagram notations for each of these devices that are on the circuit. A battery is indicated by two long and two short alternating lines as such. So that's our energy source for our electrons. As you can see, I actually broke my circuit by putting my finger on it. There we go. Now I got a complete circuit again. We also require a switch. A switch is a portion on the circuit in which we can open or close the circuit. If the circuit's open like it is right now, electrons will not be able to flow through it. If I take this switch and basically close off the circuit, then at that point the electrons can flow again. And you know what switches are. If you're in your home, you've got light switches that turn your lights on and off. That's exactly what those switches are doing. They're either allowing the flow of electrons through a circuit in your home, or they're closing off or opening that circuit so that electrons can no longer flow, so you're not getting electricity being sent to the lights, so the lights would actually shut off. As well, you require what's called a load resistor, and a load resistor is any device that is going to take the electrical energy that's flowing through the circuit and convert it to another form of energy. So this could be, as I just mentioned, a light bulb. A light bulb would be a load, and it's going to basically resist the flow of electrons when it enters that device, and it's going to convert that resistance is going to now take the electrical energy and convert it to another form of energy. In the case of a light bulb, the useful form of output energy would obviously be the light energy, but you would also understand that a light bulb is going to heat up as well. Not so much LED bulbs, but older incandescent bulbs would have gotten a lot warmer. That thermal energy would have also been another form of output energy. It would be a useless form of output energy, but it would be sort of an energy output that would have been created by the resistance of that device to the flow of electrons by reducing the current through resistance. So that's basically your four main parts of a circuit. You've got your conductive wire, energy source, a switch, and you've got the load or the load resistor, which is going to basically be the item that you're going to power on the circuit. All right. As well, you might be familiar with this. Wires in your home, if they're lying around inside, the ones in your wall may not be, but in theory, most of the electrical wires in your house should have some kind of an insulator around them. We've talked about conductors and insulators in an earlier video of this unit, and how conductors allow for the flow of electrons, metals, acids, bases, ionic compounds dissolved in water. And then you've got insulators, which do not allow for the flow of electrons, non-metals, molecular compounds, ionic compounds that are not dissolved in water. So you would have, normally a wire, that's carrying electrical flow, electrical current, should have an insulator around it to prevent the electrical current from straying outside of the circuit in what's called a short circuit. We don't want there to be a short circuit, and also to help prevent heat from resistance. That also helps as well, having the insulators there. As well, some circuits are going to be quite often are going to be grounded. So if you've ever heard the term grounding a circuit, you can have sometimes like a ground plug or a ground wire in your home. A ground wire would basically be an exit point for excess current. If there's excess of current that needs to be dissipated off the electrical circuit, the ground wire would be a safe location for those extra electrons to basically exit the circuit and then be basically grounded into a neutral substance, which in this case, generally speaking, would be like the earth. So it just prevents from an overload on the circuit to have that ground in case there's excessive charge that builds up in the circuit. It's more of a safety feature that a lot of circuits have, especially in homes where obviously safety is a major issue, and in businesses where we don't want to have electrical fires or anything like that. Okay, there's 3 units of measurement that we're going to be discussing when it comes in terms of electrical circuits. And this is a recap. This is going back to grade 9 science, but I'll quickly recap the 3 main measurements of a circuit and the units that are used for each one. The first measurement of the circuit, and I've been mentioning it already throughout today's video, is current. Current, which is labeled as I, basically refers to the amount of electrons that are flowing through an electrical circuit at any given point. Just like current in a river, the more water that's in a river, the bigger the current. The more electrons that are flowing through an electrical circuit, the bigger the current. Current is measured essentially it's measured in coulombs per second. So the amount of charge that's flowing through a current per second of the electrons flowing through that circuit. But we use another unit to measure that, coulombs per second. It's basically designated as what's called an ampere. An ampere or an amp. You may have heard of amps. That's your measurement of current, which is labeled as A. Now, amperes, just so you know, are named after André-Marie Ampère, who was a French scientist in the late 1700s and early 1800s. He made several discoveries in relation to electricity. He discovered that a wire carrying electricity or electrical current could either attract or repel another wire, depending on which direction the currents were flowing. If the currents were flowing together in the same direction, they would repel one another. If they were going in opposite directions from each other, they would attract one another, just based on, and again, the reason for that was their magnetic fields that were basically being generated. So he didn't officially make the discovery that Oersted did only a few years later. Oersted was the one who officially discovered that electrical currents generate magnetic fields, but Ampere was certainly on the right track he was certainly thinking in that direction. He just never officially, I guess, recognized the connection between electricity and magnetism. He sort of had an idea, but didn't formulate it as well as Oersted did. And Oersted obviously got the credit for the discovery of the connection between magnetic and electrical fields. So, but Ampere was certainly close in that respect. The second unit, which we use for circuits, again, another one you're probably familiar with, voltage, is basically measuring, which is measured in volts. It's basically the amount of energy carried by a current. So how much energy, how much potential is there for the electrons to flow, and how fast they can flow through the current. Volts are another unit that's named after another scientist. Again, that seems to be a real occurring theme in this unit. We've talked about coulombs, we've talked about newtons, we've talked about amperes. Volts are named after Alessandro Volta, who was an Italian scientist who developed the first battery, which was known as the voltaic pile, and that was in 1799. So he basically came up with originally the first battery that basically could power a circuit to generate electrons that could flow through an electrical circuit. So yeah, there's voltage as well. Now, sometimes in a circuit, now this is something that I already mentioned earlier, we talked about load resistors and how a load, like a light bulb, will convert electrical energy into another form of energy, like light energy or heat energy. resistors, when they're placed in a circuit, and you can place resistors in a circuit that aren't necessarily something that you're going to power, although loads by definition are resistors, but you can place resistors in a circuit to limit the flow of electrons at a given part of a circuit. Maybe there's a part of a circuit you don't want a lot of electrons to be flowing through. You can place simply what's called a resistor in there that's going to basically allow for the flow of some of the electrons, but not all of them. It's going to make it tougher for electrons to flow to that part of the circuit, because it's almost like you're placing kind of an analogy would be you're placing a dam there that's sort of blocking the flow of the electrons on that part of the circuit. And the electrons are like water that way. They're going to find the easiest way to flow through the circuit. So if you put a resistor on one part of a circuit, electrons are going to maybe flow a little bit heavier onto other parts of the circuit. So this way you can kind of control where your electron flow is. Now, regardless of that, a resistor, is going to do what resistors do, and it will essentially take the electrical energy that's flowing through that part of the circuit, and it will convert it. Generally speaking, it will convert to light or heat, or potentially both is what it'll do. So it's not like it's destroying the electrical energy that's flowing through it. We understand that it can't. That's the laws of thermodynamics. We've discussed that already. Energy cannot be created or destroyed. It can only be transferred, and that's what's happening here. If I reduce my amount of electrical energy, it's going to get converted to something else, and in this case, it would be light or heat. The more resistance, that a resistor has, the more energy the resistor gains from the electrons that are passing through it. So if you make a very heavily resistant resistor, you're going to convert a lot of that electrical energy into other forms of energy. Okay. And that leads us to our final unit of measurement, which is resistance. That is the third of the three units of electrical measurement that you would have learned back in grade 9. You've got, again, currents in amps, voltages in volts, and you've got resistance, which is the opposition to the flow of electrical current. So this is sort of what stops electrical current. It's measured in a unit called ohms, which is measured by it's abbreviated as the omega symbol, the Greek symbol for omega. It's named after Georg Ohm, another scientist who got a unit named after him here in this unit in electricity. It seems to be a real occurring theme, as I've mentioned. He was a German physicist and mathematician, and he researched Volta's battery extensively. So after Volta invented that first voltaic pile battery, Ohm basically got his hands on it and did a lot of experiments with it. And through the experiments with that battery, he was able to find a mathematical link between all the three measurements that I've just discussed here today. He discovered that there was actually a mathematical link between voltage, current, and resistance. And that became known as Ohm's Law, which if you want to take a peek, you can take a peek at this video here about Ohm's Law if you want to watch that and give it a watch to see what that's all about. But basically, Ohm's Law stated a few things. One, he said that if the temperature remains constant in Ohm's Law, a resistance of a conductor will always remain consistent. So if you have a circuit and you have a constant temperature, resistance on that circuit is going to be, or that conductive wire is going to be consistent if you keep the temperature the same. He then said that the voltage and the current would either go up or down together. So if I increase my voltage, I'm going to increase my current. If I decrease my voltage, I'm going to decrease my current. There was a proportional relationship between voltage and current. And he also discovered that there was an inverse relationship between current and resistance. If my current went up, my resistance would go down. If my resistance went up, my current would go down. And because of that, he formulated this equation. And the equation that basically is at the heart of Ohm's Law is voltage is equal to current times resistance. So V equals IR, and that can be rearranged into I equals V over R, or R equals V over I. Again, do you need to know it? I'm looking on your data sheets here. I'm not sure if it's here it is. Yeah, it's right here. Top of page 3. There it is. you get the V equals IR equation on your data sheet. So it's there. The units that are going to be used in this equation always, voltage is always going to be measured in volts, current's always going to be measured in amperes, and resistance will always be measured in ohms. Yeah, so there you go. So let's take an example using this Ohm's Law equation, and let's see what we come up with. Here's an equation for you. So if I have a current of 2 amps flowing from a 30-volt battery across a 10 ohm resistor, what voltage would be found before and after the resistance if measured by a voltmeter? So we haven't officially discussed voltmeters yet, but a voltmeter would be a device that you would place on a circuit that would measure a voltage drop over anything that would have resistance, whether it's a resistor, a load. It would indicate how much voltage is actually being swallowed up, how much energy, how much electrical energy is being swallowed up by that resistor and being converted into other forms of energy like a heat or light or whatever. So the question again is, if I have a current of 2 amps flowing from a 30-volt battery across a 10 ohm resistor, what voltage would be found before and after the resistor if measured by a voltmeter? So you're looking for 2 answers here. See if you can plug this one in, see what happens, and I'm going to tell you the answer here in about 2 seconds, right about now. Okay, so the battery has an initial output voltage of 30 volts, so we know that. So that would be the voltage found before the resistor, okay, because we know that that's the energy before I hit the resistor. It would be the output energy of the battery, which in this case is 30 volts. So in that case, I'm going to basically calculate, what I'm going to do is the voltage drop over the resistor. How much voltage am I going to lose over the resistor? I need to have I need the information about the resistor, which I do have information about, and I also know the current. I know that my current is going to be 2 amps, and I know that my resistor is 10 ohms. So technically, the 30 volt battery is my initial energy. That's my initial. That's the voltage that I start with. I don't have to do any calculation for that because they told me the battery has 30 volts. So I know that's my initial. Before I hit the resistor, that's my energy. To calculate my voltage after the resistor, I need to calculate my I times R, which would be the current of the circuit plus the resistance of the resistor, which is going to be 10 ohms. So if I would have calculated, I had 2 amps plus times 10 ohms, that's going to give me a voltage drop of 20 volts over the resistor. Is that my final answer? No, well, no, it's not. That's the drop. So I technically have to take 30 minus 10 to then calculate that after the resistor, I would have only 10 volts of electrical energy left over after the resistor. So the answer here would be the before voltage would be 30 volts, the after voltage would be 10 volts. So that's how you calculate that. And I'm going to give you more questions related to that in the video tomorrow. This was a sort of a warm-up, but the next video you're going to watch is going to be doing more of the math about how you calculate different types of resistors on different types of circuits. How do you calculate the voltage? How do you calculate the current? That will be coming up in our next video. This was sort of more just a warm-up. All right, it's time to review. Take a look at this video here just to get you kind of all wrapped up for today's concept. That's it for today. There is no questions officially assigned for this part of the lesson. Just hopefully you've taken your notes and you've gotten now the understanding of what Ohm's Law is, because it will play a heavy role as we walk into our next half of the conversation about electrical circuits, which will be next day when I discuss the difference between parallel and series circuits and how you do different calculations for each of those electrical circuits. Thanks a lot for tuning in, and we will definitely see you next time.